you can have an image that has 2 bits, 4 grayscale values, 4 bits, 16 grayscale values. With 16 grayscale values, you can see that it already starts to look a lot like these 256 here. But there's no reason to stop at 1 byte and just 256 grayscale values. Many of the modern cameras have a very large dynamic range, much larger than 256. So we need to encode that in more bits, and so we need at least 2 bytes. And for instance, many cameras have a dynamic range of 12 bits, 4096 grayscale values, or 16 bits where you have almost something on the order of 65,000 different grayscale values. Now, that dynamic range also in the end determines the image quality and determines the information content of the image. And just to give you an idea of that, I encoded an image here in 2 bits, 4 bits, 6 bits, and 8 bits. And you see that the 8-bit image looks like a real image. We see all kinds of different things here. We see detail we see some detail here in all those areas. And that detail completely disappears in this image that consists of only 4 grayscale values. So the number of grayscale values also determines the information content of the image. On the other hand, it's kind of interesting that this 4-bit image already looks a lot like the real image. Remember, we have only 4 grayscale values here. Works already pretty well. And when you look here, 4 bits starts to look better, but this looks still quite pixelated. But here with the 6 bits, so that's just 64 grayscale values, looks here on my screen almost the same as the 8-bit image. So the human eye and displays like this actually cannot discriminate more than roughly 100 different grayscale values. And that's why these 8-bit images are often good enough to present themselves very well. So, as I already said, a monitor, the displays you use on your phone, your computer, in general has only can only display 256 different grayscale values, and that is fine because your eyes, your accommodating eye, can actually not even discriminate each of those from each other. But that also implies something funny, because if you now have a 1-bit image, it has a value 0 and a value of 1. If you just put that directly on that 8-bit display, you will see that both values are black. So the value 0 is black and the value 1 is black, because the 8-bit display, you see that shown here, is that all these low values will have a very dark way of displaying. And so conversely, if we have these images that have like many grayscale values, so the 12-bit image, for instance, with 4096 grayscale values, everything higher than 256, if you display that on your monitor, will be white. You can't see it. And so that means that we need a way of mapping these pixel values that we have in our image onto the monitor that can display it. So we don't want to change the underlying values, we just want to change the mapping from those values onto the monitor. Now, so in practice, the way you do that is often by manipulating a function that looks something like this. So we have a function that maps the original intensity. So here, this is a 12-bit display image going from 0 to 4095. And we map that to the display on the monitor. And the simplest way of doing that is to use a linear mapping. So we set 0 in the original image to 0 on the display, and we set the highest value, 4095 in the image, to 255, the highest value on the display. So if you do that, you have to be aware that you're not seeing all the detail that you have in the image. For instance, all the values between 4080 and 4095 will only shown on the monitor as pure white, as 255. So often you want to manipulate this function so that it brings out all the detail that you have in the image. And so manipulating this function you often do by moving the maximum or by moving the minimum. And when you move each of these by themselves, what you change is the slope of this line. And when you change the slope of the line, that will change the contrast that you see in the image. For instance, if you now start to make lower pixel values white, then the brighter areas of your image will get whiter and whiter, whereas the dimmer images of the area of the image will stay the same, so it will increase the contrast. So when you move the minimum and maximum simultaneously, what you will be doing is changing the brightness of the image. So another tool that is very useful when you are manipulating image display is the histogram. So a histogram will display for every grayscale image, for every grayscale value in your image, how many pixels there are that have that specific grayscale, that have that specific number. So we have here on the y-axis the number of pixels, on the x-axis is the pixel value. And you see here that at this specific grayscale value we have a lot of them, so that's probably the background here in our image. And so often you use this histogram to match the maximum and minimum. You set the maximum to the maximum pixel value in your image, the minimum to the minimum pixel value in your image, and you already have a very good starting point to look at what is going on in your image. Just to give a few examples, we have here another Drosophila spindle image. When we now scale this to the minimum and maximum as I described, you see the kinetical fibers and you see some detail here elsewhere in the cell. You can now make that come out a bit more by moving that maximum, so that makes the image brighter, it increases the contrast. If we now move also the minimum here, then you see that the darker areas of this image are totally being clipped off and it disappears. So we have here an even higher contrast and we start to lose some of the information here, but we possibly can make out a bit more of what's going on with these brighter kinetical fibers. So each of these ways of displaying the data is in a way equally valid. When you compare images with each other, it's very important that you use the same brightness contrast settings, otherwise you don't know what you're comparing with each other. And in general, you really should be sure that if you want to use your images to make a point to others, that you describe how you are displaying the data. color images. So color images in the computer are basically treated as individual grayscale images, where we now have for an RGB data set, we have a red image, a green image, and a blue image. Each of the in the computer memory sees it as rows and columns of numbers, that then where we just arbitrarily say, okay, this one is going to be displayed red, this one green, and this one blue, and when we combine that all together, we get back our RGB image. And just like monochrome images, RGB images can be stored with in 1 or 2 bytes per channel. Most consumer-grade channels will be 1 byte per channel, but when you go to SLRs with raw images or professional-grade RGB cameras, they can have a much larger dynamic range and use 2 bytes per channel. File formats. So once you have your data in the computer, you want to store them one way or another on disk, such that you can also exchange them with other people. What is important to remember here is that many of the file formats will try to compress the data for you. Compression is nice because it reduces the amount of data that will be taken up on the hard drive. However, some forms of compression will no longer allow you to restore the original data, and that is bad because you won't later be able to know exactly what the camera has measured. And so therefore we have terms for this. One is lossy compression. So lossy compression, we lose data, we can get it back again. Lossless compression is a compression where you do not lose data, so you have a way of restoring the exact original image content. So lossless compression is okay. Lossy compression is not good if you want to continue your analysis. The file format that is widely used is the so-called TIFF format. TIFF is a container format. There are many different ways of storing your data within a TIFF. You can have 8 or 16-bit data. You can have it can incorporate lossless compression. It supports grayscale as well as RGB images, and in general, TIFFs are really a nice way to store your data. You can exchange it easily with others. There are a bunch of there's a whole lot more actually than these more proprietary data formats. And so the people behind this have decided to make a tool that is able to read all these different file formats, but also the hundreds more that are out there and that the different microscope and camera companies have come up with. And so with this bioformats that's used in many different software packages, including ImageJ, you can read more or less anything that you encounter. So super useful software. Now when you have your digital image, you will want to measure something, and often the following way is taken to do so. It's done by segmentation, and in segmentation what you do is to create a mask of things that are in and conversely things that are out. So the mask is a binary image, so it just contains 1 bit per pixel, and when it's 1, that means it's in, and when it's 0, that means it's out, so it's background. And the easiest way of segmenting is to look at your grayscale values and move a slider and say everything below this specific grayscale value is out and everything higher than this grayscale value is in. And that's how you can do a segmentation like this, where you see that these spots correspond pretty nicely to what you see in your dot plot. There's also some junk here, little things, and there's some binary manipulation techniques, erosion, dilation, where you erode your pixels in and then dilate them back out again so that they restore the original. But then things that are too small simply erode out and disappear. You can see that you can nicely clean it up, and now the spots correspond very well to the spot in the dot plot. So measuring objects then often consist of starting out with the image, do a segmentation so that you can get masks that correspond to the original objects. You now, each of these masks you put over the original image and you ask what were the grayscale pixel values there. You can get out the total number of pixels, the mean, the integrated density, and you get then a list with the intensity under each of these objects, and that already can give you a very clear idea of what is going on in this image. Now this is a very simplified way to show you how measurements work. Just to give you an idea, there's more and more image analysis being used in biology. For instance, this is here a very recent publication in Nature Methods, where the authors developed a method to automatically determine sites of mRNA, as mature mRNA as well as nascent RNA in images obtained by fluorescence in situ hybridization. So it goes to show how an automated image analysis procedure can give you very quickly and easily biological insights extracted out of the image. And another example I want to show you comes from this RNAi screen that we did, that our group did a few years ago in Drosophila S2 cells, where we were looking for genes affecting mitotic spindles, and where we used these kind of image analysis techniques to automatically detect mitotic spindles in the images that we acquired, and to measure various aspects, like for instance the distance between these poles, to get an idea of the spindle length. Now I hope you got a basic understanding of how digital imaging in microscopy works, and you know, go ahead and play with these techniques yourself and have a lot of fun with it. Thank you. So much of the microscopy that we're doing nowadays is fluorescence microscopy, and I'll be explaining what that is in this lecture. So why do we use fluorescence in a microscope? As you've probably seen so far, there are two important aspects in making a great picture in a microscope. One is resolution, you want a high resolution, and the second thing is contrast. You want high contrast, otherwise you wouldn't see anything. And what fluorescence offers is this high contrast. So it's demonstrated in this image here. We have part of the cell labeled in green. In green we're looking at microtubules, so we label microtubules with a fluorescent dye, and we have part of the cell labeled in red, and that part is actually the nucleus, or if it's DNA, it's a red label attached to the histone protein. And what you see is that this label stands out on a black background, so we have a very high contrast. We see what we want to look at, whereas our background is totally absent, so it gives an actually extremely high contrast. And what we also already see in this specific image is that you get specificity. We can attach these fluorescent labels to specific proteins, to specific molecules, to specific dyes, to specific places in the cell or wherever we want them, so we can target them, but they show what we want to see. Then fluorescence is quantitative, so if I calibrate my system correctly, areas where we have higher signal, like here, those are areas where I have more of my the protein that I'm interested in. So in this case, there's a lot more tubulin here in this bright area than starts playing those faster, we see that it's actually a dividing cell. So the microtubules assemble in this spindle, and that spindle then pulls apart the chromosomes into two daughter nuclei. So fluorescence is a great thing for microscopy, but what is it really? And what's kind of surprising to me still is that humankind has been aware of fluorescence for only about 150 years. So one of the first descriptions of fluorescence was by Sir William Herschel. He was studying the aspects of an extract of the bark of the cinchona tree, and he held up this extract in the light of the sun, and it came through his window, and he noted that the light of the sun induced a celestial blue light coming out of that extract of the bark of the cinchona tree. And I will now try to repeat that 150-year-old experiment here in the lab, and I'll be showing you that now. So the bark of the cinchona tree is hard to come by, but luckily the active ingredient can be found in every supermarket in the form of contained in tonic water. And so I'll take this tonic water, put it in a glass, and then the other part is that we need UV light to illuminate it, and that you can buy in the form of what's called a urine tracker in the pet store. And so when we now shine this UV light in the quinine, or in tonic water, and you see that you get a blue light emanating from within the tonic water. It's another wavelength, it's a longer wavelength than this light with which I illuminate, and that's why we see it a lot better. Our eyes are not very sensitive to this UV, but they are highly sensitive to the blue light in the tonic water. Quinine is not the only compound that fluoresces, of course, so it's really quite interesting. Already in the 19th century, scientists synthesized this dye called fluorescein that is highly fluorescent, and when I shine blue light in that, we get yellow fluorescence coming out. And another very well-known dye is rhodamine, and when you shine green light in that, you get this orangey, yellowish fluorescence coming out. And so this is fluorescence. Okay, so what we've seen is that we use light of a lower wavelength, so in this case of the quinine from the extract of the bark of the cinchona tree, we use UV light, and then the dye responds to that light by emitting light of higher wavelength, so in this case blue light. So in general, except for very special cases, emission light is of a longer wavelength, that means lower energy, so there's some energy loss going on in this process than the excitation light. Now this aspect of fluorescence is very important, and we often show that by measuring the spectrum. So we measure an excitation spectrum, which is often very similar to an absorption spectrum, and we measure an emission spectrum, so here, that's this curve here, which is the fluorescent light emitted by the dye. So we characterize these dyes by their excitation maximum and by their emission maximum. Those numbers tell you immediately a lot about how to use the dye in your actual experiments. The difference between the excitation and emission maximum is called the Stokes shift, after Sir Stokes, who first realized that there was this difference. And you can have dyes that have a small Stokes shift, where the emission is very close to the excitation, or you have dyes with a large Stokes shift, where the emission is very far away from the excitation light. Now, so there's energy loss going on, and that causes this difference in wavelength. But how does that happen? And one of the most useful ways of thinking about that is through these so-called Jablonski diagrams. Jablonski was a Polish scientist who did this work at the beginning of the 20th century. And in these Jablonski diagrams, we use we're looking at the orbitals that electrons can be in. When an electron when a dye absorbs light, that electron is going to be kicked in a higher orbital, in a higher energy state. This absorption goes very, very fast, so it happens at a time scale of femtoseconds. And femtoseconds to me don't mean much, so I like to express this in the distance that light travels during that time period. And since light goes extremely fast, so it's pretty amazing that light travels only like 0.3 microns during this time period. And once that electron finds itself into these higher orbitals, through a process called internal conversion, it quickly falls back to kind of what you could call the ground level of the excited state. And that internal conversion is a tiny little bit of heat that dissipates this way, so we have a bit of energy loss here. And that happens on the level of time scales of picoseconds. And light would travel only 0.3 millimeters during that time period. Now, then the electron can hang out here for what is, in comparison to these previous time scales, almost eternity, something on the order of many nanoseconds. And then it will fall back to the real ground state and emit a photon. And that photon will be of a wavelength less than the wavelength that was, of an energy that is less than the energy that was put in initially. And that means that the photon that's coming out is going to be of a higher wavelength. Now, not only, this return to the ground state is not the only process that can take place when a dye is in the excited state. It's also possible that the energy is transferred to other molecules, or even it can return to, the electron can fall back to the ground state, but not emit a photon. So there's also non-radiated decay. So we have a total number of events, some of which result in light coming out, some of which that don't. And we express the ratio of those two as the quantum efficiency. And the quantum efficiency is a very important parameter of the dye. It not only depends on the dye itself, it also depends on its environment, for instance, what other molecules are around the dye. But nevertheless, quantum efficiency is something you want to know and that you want to measure, or that you want to be told what it is. Another important aspect is the brightness. And the brightness, in the end, is determined by how well the dye absorbs the excitation light and what fraction of the excited state returns to the ground state under emission of fluorescence. So it's determined by both the absorption coefficient and the quantum efficiency. Now, another important aspect here is what we already talked about. How long does it take between absorbing a dye and for the dye to return to the ground state? And that is what we call the lifetime. And so it's mainly determined by how long it takes before we return to the ground state out of the excited state. So usually this is on the order of nanoseconds. Nevertheless, it's also a parameter that is dye-specific, that is also dependent on the environment of the dyes. And there's a whole form of fluorescence microscopy called lifetime microscopy that actually reads out lifetime instead of only reading out the fluorescence itself. Nevertheless, what we're now going to talk about is microscopes that discriminate between the excitation light and the emission light. So how do we do that in a microscope? Well, the main thing is that we use filters. So we use filters that filter the exciting light so that we get out of our light source only the light that is of the wavelength that will excite our dye. That light will bounce off the dichroic mirror and then excite our sample after it went through the objective. The sample will start fluorescing, and that fluorescence then travels back through the same objective. It will now pass through the dichroic mirror, and then there's an emission filter that will let through the fluorescence, but that will completely block any scattered excitation light so that we will only see the fluorescence on our detector, which I symbolized here with an eye, but that could also be a CCD camera or whatnot. And so this is the simple, basic principle of a fluorescent microscope. So the most important aspect here, and the thing that makes it different from a normal microscope, is filters. And these filters need to be very good because they really need to discriminate this excitation light from the emitted light. So what options do we have there? Well, you can have filters that are based on absorption, that absorb certain wavelengths of light. Those are not that great in practice because their spectra are very broad, so they will also absorb a bit of the emission light if they're, so that they will not exactly do what we want them to do. And the type of filters that we mainly use these days are interference filters. So what are those? Interference filters are basically thin alternating layers that have different refractive index, so that we get interfaces there that can reflect the light. So we can almost think about them as thin transparent layers that are about the wavelength of the light, or half the wavelength of the light, with semi-reflective coatings in between. So what now happens when light hits this filter is that part of it will be reflected, part of it will move through. The light that reflects will interfere with itself, and when the wavelength is such that it matches the wavelength of the light, you will get constructive interference. And that constructive interference will then in effect let the light pass through this filter, whereas when the wavelengths are different from the two, the distance between the layers, we get destructive interference and it will be reflected out. Now the filter manufacturers can completely compute how these layers will behave, so they can design in the computer what wavelengths this filter should pass through and what wavelengths should be reflected. And you can basically order any type of filter that you may possibly need. Now, just to make this a little bit more clear, there's one example of interference that you're highly aware of and that every one of us have seen, and that is what you see in soap bubbles. So in soap bubbles, when light hits that, you will see reflection of all kinds of colors of light. The soap bubble itself is a thickness that is on the order of half the wavelength of a lot of the visible light, and we will get the same interference effect where some of the light, some of the colors will pass through and other colors will be reflected, and that gives these beautiful colored patterns. Now, we will break and show you some of these filters, and we'll also show you now here how these filters are assembled in a filter cube. Okay, so I have an example here of such an interference filter. This one is called a HQ47030, and the 470 is the center wavelength of this filter, and 40 means the bandwidth. So this one will pass blue light. And so if I have my blue